with these expressions for acceleration, velocity and displacement, as the particle moves at various positions for the given time interval, when the particle is at the mean position, its displacement is always 0. If the displacement is 0, then if we check the relationship for the velocity, then velocity of the particle at mean position V will be equal to plus or minus omega under root a square minus the value of x will be 0. So V will be equal to plus or minus omega under root a square will be a. And so this will be a maximum velocity possessed by the particle when it is performing simple harmonic motion. And so we can treat this velocity as maximum velocity, we'll mark it as Vmax. Because for any other position, if the displacement is some numerical value, it will get subtracted from a square and then the value will be the smaller value. Now if x is equal to 0, then acceleration minus omega square x. For the mean position, the value of x is 0, so acceleration becomes equal to 0. And so we can now record values for x, v and acceleration number 1 at mean position. At mean position, displacement x, it is minimum and it is equal to 0. Velocity v, it is maximum and it is given as plus or minus a into omega. A is the amplitude, omega is the angular velocity. Acceleration is minimum and it is equal to 0. So these are the conditions when the particle is at mean position. What happens if the particle reaches the extreme position? Either over here or here. So at extreme position, x is maximum and that is equal to a, which is equal to amplitude. So this is the maximum displacement which the particle can perform, and so x will be maximum. So displacement maximum is equal to a, that is the amplitude. Now if the particle reaches the extreme position, then the v value will become v is equal to plus or minus omega under root a square minus, now the value of x is a, so this will become a square. So v will be equal to plus or minus omega, a square minus a square will be 0, and so v minimum will be 0. So when the particle reaches the extreme position, either towards the right extremity or toward the left extremity, or if the vertically it is moving, if it reaches the top position or the bottom position, velocity minimum or velocity becomes equal to 0. For acceleration, acceleration is minus omega square x. So acceleration is maximum at extreme position, and so it will be minus omega square a. Negative sign indicates that when the particle reaches the extreme right with maximum displacement x is equal to a, acceleration is directed toward the mean position. And so in this way we will have one more set of expressions. At extreme position, displacement x max, this is equal to a, that is the amplitude, velocity v minimum 0, and acceleration max, this is minus a omega square. And so these values are very important when we solve the problems considering the particle at the mean position or extreme position. These general values are when the particle is anywhere at any position in between mean position and extreme position. Yes. So when we are considering x is equal to a sine of omega t plus phi or alpha, whatever we will take the denotation as the displacement of the particle performing simple harmonic motion. Omega t is the phase of SH. Yes. Now, if the sine of omega t plus phi for sine function, the maximum value is plus 1 or minus 1. The value of sine as plus 1 or minus 1 if we take, then the value of x becomes equal to a plus or minus a. This is the maximum displacement which the particle can perform. And so amplitude of SHM is defined as the maximum displacement of the particle performing simple harmonic motion. And so from mean position, when the particle gets displaced to the maximum distance of A on toward the right hand side or towards left hand side, this maximum displacement will be denoted as amplitude of SHL. Yes. Now we know that oscillation is a periodic motion. As it is periodic motion, the particle is going to come to the same position again and again. Say if we consider about the mean position, the initial or the starting phase phi will be 0. And so the expression for displacement when the particle is at the mean position, we are able to write it as A sine of omega t. Or if we take the particle anywhere over here, then we can also introduce the initial phase as phi. If initial phase is 0, particle will be at mean position, displacement will be x is equal to A sine of omega t. If it is at any of the position other than mean position, x will be equal to A sine of omega t plus phi. Now as the time increases, say as the time is having an increment, T1 will be T plus some value. As it goes on, let us consider this increment as 2 pi upon omega. So, if this is T1, then what will be the value of the displacement? X1 will be A sine of omega T1 plus phi. So this can be written as A sine of omega into bracket T plus 2 pi upon omega plus phi. So this can be expressed as A sine of omega t plus 2 pi omega upon omega plus phi. So this can be expressed as A sine of omega t plus phi plus 2 pi. Let this angle be A and this as B. So we know the formula sine of A plus B, sine of A, cos of B, cos of A, sine of B. A is written as omega t and B as 2 pi, then we know the value. Cos of 2 pi is 1 and sine of 2 pi is 0. So it comes to be sine of omega t. So if this angle is omega t plus phi, then by using this particular formula, this will be sine of omega t plus phi. This is nothing but x. So here what we consider if the increment of the time is 2 pi upon t, then particle comes to the same position on the path of SHL. And so if the particle starts from here, after time 2 pi upon omega, it comes to the same starting the same starting position. If it starts from here, after time 2 pi upon omega, it will be at the same position again in a same state of vibration. And so, as the particle return back to the same state of vibration after the time t is equal to 2 pi upon omega, this is called as period of SHM, and period of SHM, which is denoted as capital T, is 2 pi upon omega, where omega is angular velocity, it is second or S T. We also know omega square is k upon m. So omega can be expressed as root of k upon m, where k is the first constant. So the period t can also be expressed as 2 pi upon under root k upon m, or the period can also be written as 2 pi root of m upon k. So this is the first constant. So period is expressed as 2 pi root of m upon k. We can also express this as in terms of acceleration, because this is force per unit displacement. So if we cancel the value of m, this becomes acceleration per unit displacement, and so k upon m can also be written as acceleration per unit displacement. So the value of t can also be written as 2 pi upon under root acceleration per unit displacement. And so period of SHM is t is equal to 2 pi upon omega, or t is equal to 2 pi upon root of k upon m, where m is the mass and k is the first constant, or 2 pi is equal to root of m upon k, or t is equal to 2 pi upon acceleration per under root acceleration per unit displacement. Here we can define the frequency. Frequency is the number of oscillations or number of vibrations performed per second. So frequency F is equal to 1 upon T. So this will be 1 upon 2 pi upon omega. So this will be omega upon 2 pi. Frequency is having a unit hertz, or it is also written as number of cycles per second. So F will be equal to 1 upon 2 pi. Omega can be expressed as root of k upon m, where k is the first constant. So F can also be written as 1 upon 2 pi root of acceleration per unit displacement. So here we have seen the important relationships, important definitions as amplitude, period and frequency.